In this video, we'll be finishing our lecture set by discussing measures of variability or spread. So, finding the middle of a data set is often not enough information for many applications and interpretations. Consider this example. I'm at a coffee shop and I'm told the wait time is 5 minutes. This might not seem very bad at all. But later I might discover that, in fact, the wait time is 0 minutes for many customers, and other customers wait half an hour. Well, now I might realize that maybe that 5 minutes on average isn't really what I'm looking for. It could work out really well that I'm in and out very quickly, but also I may be forced to wait. As someone who often have places to be, and frankly, as someone who typically has kids in the car, I'm not going to risk waiting 30 minutes. Maybe I'll find a different place. On the other hand, consider if I found something, a different measure of spread here. I go to a coffee shop that's 5 minutes, and I find out that every customer gets their coffee in exactly 5 minutes. Whether you order a latte or whether you order a black coffee, you get it in 5 minutes. That might be really good information, and maybe for me, it's something I could plan on, and that consistency is really important. I wasn't planning on talking about this example, but here at the university, we have a restaurant on campus that sometimes takes some time. On the other hand, they do tend to be very consistent. So one of my strategies that I've done in my daily life is I will give them a call and make an order and then go pick it up after, that set amount of time, because they're pretty consistent about what that set of time needs to be. Now, the thing is if they're not consistent, I can't really trust that. But if they are consistent, I can plan ahead for that level of consistency. That idea of consistency is kind of the opposite of spread. If you're not spread at all, you're very consistent. You tend to do things the same. That is, if I went in multiple times to that restaurant, they tend to make me wait about the same number of minutes every time. On the other hand, if it's very spread, sometimes I wait 0 minutes, sometimes I wait an hour. I could not do what I do right now, which is put in an order and plan on it being ready after a certain amount of time, because it could be ready right away and then my food would get cold, or I could head over there and it's not even close to being ready. It'll be another hour. So that is a good example of levels of spread. For maybe a more serious example, consider heart rate. If you come on shift, and in the shift handoff here that the average heart rate is 70 beats per minute, that could tell two very different stories. One story is it's 70 beats per minute every measurement, or 69, maybe 71, maybe 68. A second story is it's 40 beats per minute half the time and 100 beats per minute half the time. Those would be two very different stories, but both would have the same quote-unquote average or central tendency heart rate. All this is to say there's something that distinguishes this. That is, between 70 beats per minute every measurement and 40 half and 100 half, there's something that's different between those two. That difference, and of course the importance of this concept, is the idea of spread or variability. Now, the reason I prefer the term variability here, because it varies, things change. And think about think about taking your hands and kind of clumping something together like you're making a little snowball, and then spread your hands out. And think about your data being a whole bunch of little particles that are kind of clumped together in a snowball or are spread out like a whole bunch of snowflakes falling down from the sky. Like, that is the difference between that's the effect of spread or variability. And it's a very important concept in terms of making important or correct decisions based on data. All right, so the first measure of variability or spread is the range. So I mentioned earlier, I prefer the term measure of variability. The variance is a very specific term in statistics referring to one measure of variability. So sometimes people call this measures of spread, in place of measures of variability so that we don't get confused with that term variance. I'll use spread and variability interchangeably with the knowledge that I will say the word variance very specifically when we talk about that concept later. So just a heads up. In any case, the range is the simplest of the measures of variability or spread. Range just asks how far did the data spread? Like what's the largest value, what's the smallest value, and how far apart are these? So if you think about that example with your snowball and you spread your hands far apart, range just asks how far apart do you spread your hands? Are they really close together? Like if you come in to do a clap or you're, talking about something very, very small, or are they very far apart when you're talking about that fish you caught last weekend? So in this case, we look at the biggest number, we look at the smallest number, and we subtract the smallest number from the biggest number. And that's how we calculate spread. And that's it. That's really all that's needed for the range. Well, this is a really simple calculation. The downside of this calculation, so the upside is that it's simple and it's quick. And it's informative in its way. The downside is that it actually throws away a lot of data. So if you think about this for a second, the data that we have here in the range, we only use two numbers. We use the biggest number and we use the smallest number. And that's it. We don't use any of the other data points. We just keep two data points. So we might have 1,000 data points and we throw them all away except for two. And this is not particularly a good thing. So that's the downside of range, is that we don't always have it's not the most descriptive, and it doesn't really account for the clustering or the spread or variability or how condensed data are. It doesn't account for any of these things for the rest of the data, just the biggest and the smallest. Also, again, because it just looks at these end values, if I have an outlier that's way, 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 way out there, range is very easily skewed by that. All right, so let's do a couple examples. As before, again, you're welcome to pause at any time if you want to try my ones. Just go on, and once you see the data, go on and pause and calculate it out yourself. But here, I'm going to calculate the range of the below salaries in thousands of dollars. So we've got salaries of non-physicians here. The top salary, and this is a bit edited, but the top salary here is $99,500, and the bottom salary is $41,000. Thus, the range in salary, that is how spread out are the salaries, are $58,000, $58,500. That's how spread out our salaries are. And that's it. I find the biggest number, find the smallest number, subtract the smallest from the biggest. All right, now you give one a shot. Go on and pause the screen. Give this one a shot, calculating for physician salaries at a particular small institution. All right, coming back to it, we find the biggest number. For me, I find the biggest number to be 422,000. We find the smallest number. For me, I find the smallest number to be 190,000. So I take this $422,900. $190,200, and I subtract the two, and I get the range in salaries is $232,700. All right, a second measure of variability is the interquartile range. So remember we calculated the quartiles earlier. The interquartile range, or the IQR, is also relatively simple. It involves calculating the quartiles, and once we have the quartiles, it's really easy. The advantage of this one is it's less influenced by outliers. So to calculate it, we really do just calculate the quartiles, and then just like with the range where we subtracted the minimum from the maximum, here we subtract Q1 from Q3. That's it. That's really all we do. So we calculate Q1, calculate Q3, and do Q3 minus Q1. This measure of spread, so I guess we didn't mention this earlier, but some measures of spread are often presented with particular statistics. The range and the IQR, sometimes interchangeably, but most often the IQR is presented when we present the median. So if I'm using the median as a value, say I've got some outliers in data, I would present the interquartile range as my measure of spread. So this value is, again, less influenced by outliers. And in fact, what's interesting, some of the outlier formulas that determine like what actually is an outlier, how far out do you have to be an outlier, use the median and interquartile range to make that calculation. So interquartile range are so much less influenced by outliers that some people use them to define what even is an outlier. All right, so let's try this. Calculating of the below salaries again. So we have, again, first step, find Q1 and Q3. So remember what we have to do to find Q1, Q3. Don't just go on and say, oh, I remember this. 25, we've got 10 data points. 10 times 25 is 250 divided by 100 is 2.5. Round up to 3. I do the 1, 2, 3 data point. Hey, Dr. Florin, I got it. It's 62,500. I got Q1, and now I'm going to go do Q3. Be a bit careful here. Remember, what's the first step in doing this? Well, the first step in doing this is to order the data set. Remember, Q1 and Q3 and the median are all calculated for the ordered data set, so we have to put them in order first. Now we can go on and do the process. Take your n times p over 100. N is 10, our number of data points. P for Q1, the 25th percentile, is 25. Do that, we get 2.5, round up to the third position, and we find that 50,400 is Q1. Doing a similar process to find Q3, we find 75,400 is Q3. And now to find the IQR, we find the difference between these two. Q3, 75,400, minus Q1, 50,400, gives me $25,000. The interquartile range of this data is $25,000. Again, that's Q3 minus Q1. All right, now you go on and give one a try. So this is the data set you were working with last time. Go on and pause the video and then give this one a shot. All right, coming back to it. First, we find Q1 and Q3. So in this case, we only have 9 observations. I think I pulled one so that you could get some practice with a different number. We, again, first put the data set in order. And if at any time you're like, oh my gosh, I forgot to put the data set in order, yo, go on, pause the video right now and retry. Get that practice. Remember, the goal is to practice. And the goal of practicing is to get you a better grade. My goal is for you to get this and to succeed. So don't say, oh man, I missed it. Well, I guess I'm just never going to do it. Say, oh man, I missed it. Pause, practice, practice, practice. So if you forgot to put it in the order data set, pause the video. This is true for all the videos. But if you forgot to put it in the order, pause the video, give it a shot, and then come back to it. But if you do remember, great job. Thank you. So we've got Q1. I work out Q1 to be in the third position again. So that's 254,900. In this data set, I work out Q3 to be in the 7th position, 323,600. Now, I do want to call out that for Q1, and I skipped over this 2.25 is not rounded up in regular math. But remember, we always round up in this particular calculation. So this is a weird thing about this calculation, but we always round up, even if the decimal isn't normally rounded up for this calculation. I don't want you to think that this is for math or this is for statistics or anything like that. It's not. It is specifically within the calculation of the median and the quartiles and more generally in percentiles. So when we're doing these formulas, this is always rounded up, but it's just for these formulas. So if that looks a little weird, it is a little weird. You're absolutely right, but don't forget to do it. So third position, 7th position, 254, 323, and then, of course, for the IQR, we subtract the 2 and get 68,700 as the interquartile range. All right, last but certainly not least are the variance and standard deviation. These are two of the most important and most common measures of spread and variability that are used in statistics. I cannot overstate the importance of these concepts, so I beg that you pay close attention and that you do your utmost to learn these early and deeply so that when we continue to talk about them for the rest of class, and we will, these are going to be very familiar to you. Not learning these at this stage, I would worry, might make some of the other concepts unapproachable in a meaningful way. So variance and standard deviation, two of the most important things that we're going to talk about in this class. So as I mentioned earlier, variance is a specific calculation in statistics, and it's used to quantify this variability or spread. But it's not just any number. It is a very specific calculation. This calculation is very closely related to the standard deviation. So honestly, these often go together. There is a very simple conversion to go from one to the other. Yes, there's a very simple conversion to go from one to the other. Typically, depending on the context, we might present one or the other. We typically don't present both. But think about like Fahrenheit or Celsius. Maybe one place I might use Fahrenheit, one place I might use Celsius. It's kind of an okay example. It's not a great example. But again, very closely related, kind of talking about the same concepts with a very simple translation to go between them. Actually, even simpler than the Fahrenheit to Celsius formula, because I never remember that one. So where the IQR, the interquartile range that we just talked about, pairs well with the median, the variance and standard deviation are often reported with the mean, very often. They both have good theoretical properties that make them nice. Again, depending on the context, one versus the other. Typically, we use the variance for the theoretical properties and the standard deviation for the interpretation. I will say, though, that variance and standard deviation are more influenced by outliers in the interquartile range. They are not as influenced by outliers as the range is, because variance and standard deviation account for all of the data. And recall that the range just accounted for the two endpoints. But when we do have outliers, they do have a direct impact on the variance and standard deviation, very similar to how they had an impact on the mean. So typically, if we have outliers or we expect outliers in the data, we have to make a decision. Do we want to use a mean type measure of central tendency, which includes the outlier in a meaningful way? Or do we want to use a median type central tendency that addresses kind of the more broad, typical chunk of data that doesn't include the outlier? So if we want it included, we tend to go with mean, variance, standard deviation. If we don't want it included, we tend to go with median and interquartile range. Also, if we don't have outliers, we do tend to default to mean and then their corresponding measures of spread or variability, which are the variance and standard deviation. So this does tend to be the default. And again, has very nice properties that we use often in statistics. This said, the formula is more complicated. So let's walk through it. We won't jump at the formula. We're going to start slow, so stay with me. To calculate the variance, we first calculate the mean, x bar. All right, with me though so far? Okay, so calculate the mean. Then we subtract the mean from each of the data values. So for every single one of those x sub i's, every single data point, we do that data point minus whatever the mean was that we found in step one. Okay, so we've got a whole bunch of values minus the mean, so we get a whole bunch of new values. The result of a subtraction problem is called a difference. So we get a whole bunch of differences. All right, now we square these differences. That is, I take all of those results and I raise them to the second power. Okay, second to last, we add all of those up. So I take all of those things that I just raised to the second power and I add them all up. And last but not least, I divide by n minus 1. So on the denominator is n minus 1. The reason why we divide by n minus 1 is not something I'm going to go into in this class. I will say it is the difference. The n minus 1 is a sample calculation. The n is a population calculation, but we won't talk about this in this class. All right, so as you can see, this is a little bit more involved. It's not too bad, I don't think. Again, just break it down in the steps. It's not too bad. Recall what I said in one of our earlier videos. The complex part here isn't necessarily typing it into your calculator. Everybody can do the subtraction problem. Everybody can raise something to the second power. Everybody can add things. That's not what I'm worried about. Everybody can divide. It's just putting it kind of all together step by step. That can be a little more complex. We will be, again, you're going to be able to use Excel. You're not going to have to use your calculator, save for if you're following along with a calculator on this. So hopefully even that won't be too bad. And I do recommend you follow along with these, as y'all know. Notation for the variance is S squared. And so that's the sample notation. The little O with a tiny little flag on it is the Greek lowercase sigma squared, and that is the variance for the population. So this is the formula for S squared, the sample variance. I guess I did mention population calculation is slightly different in that the thing you divide by in the last step is n instead of n minus 1 in the population calculation, which again is a bit beyond our scope. All right, so put together the final variance equation is this: the sum of x minus x bar, quantity squared, divided by n minus 1. So remember, I had to write out half a page of steps here, and it's expressed much more succinctly like this. Add up x minus x bar, raise that difference to the second power, add it all up, and then after you add it all up, divide that sum by n minus 1. So it's a lot quicker to write out in an equation. And again, this is S squared, the sample variance squared. Looking at this, the numerator of the variance is a bunch of distances. It's each data point, x sub i's distance from the mean, and they're squared. What's interesting about this is this quantity is actually pretty useful. And when you square it and add it all up, this pops up in a couple of different places. You'll hear of sum of squares, where we do this kind of concept. We look at distances, we square them, and then we add them all up. So these are sums of squares. In this case, because we do it for every single data point and compare it to the mean of all the data points, this is called the total sums of squares because we're looking at all of the data and the mean of all of the data. One thing about this, we talked about kind of the interpretation of the range. It's the largest to the smallest. It's how big it is, how much spread it is. But here with the variance, the units of the variance are squared. So I take my x minus x bar, that is in my regular data units. So units is a big word. Let's say I'm looking at amount of blood loss. So and let's say I'm going to use some measure of liters of blood. So in this particular case, I might look at these measures of liters, and I would, after finding a measure of liter minus the average blood loss, my units are still in liters of blood. But once I raise it to the second power, the units in the numerator become liters squared. So the original units are no longer what we're talking about with the variance. It is those original units squared. And because of this, the variance isn't really interpretable. We don't interpret the variance as is because, again, those units don't really make any sense. So it's got some nice theoretical properties, but isn't particularly interpretable. We'll address that again in a moment. All right. First, though, let's try it. Because this calculation's a little more intense, let's use a relatively simple data set, just 3 data points. So again, my first step, I'm going to calculate the mean of these data points. So I do my old mean formula, sum of x over n. In this case, that works out to 38. The mean of this data is 38. Now I subtract the mean from each value. So I take that first value, 48, and subtract the mean, 38, to get 10. Take the second value, 26, subtract the mean, 38, and I get negative 12, and I remember the negative sign. I take the third value, 40, subtract the mean, 38, and I get 2. So at the end of this step, I get 3 new numbers, x minus x bar. These 3 numbers are 10, negative 12, and 2. The next step is I raise all of these to the second power. So I do this with the new numbers that I got in this step. I have 10 to the second power, which is 100. I have negative 12 to the second power, including the negative sign. That is positive 144. Remember, when I raise a negative number to the second power, it turns positive. So negative 12 squared is positive 144, and 2 squared is positive 4. Now, quick gut check here. Because we've raised stuff to the second power, none of these numbers now should be negative. 100, 144, 4, and any other number that's a result of this step will always, 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 now and forever, be a positive number. So all of these should be positive. Next, we add these together. So 100 plus 144 plus 4 gives me a total of, I wrote 246, didn't I? Uh-oh. What does that really give me? Why don't you cross that out and write the total correct number on your sheet? Because evidently I can't add my own lecture slides. I apologize. But yes, this doesn't actually give 246. This gives a slightly different number. And last but not least, hopefully you can calculate something that's better here, because I sure can't. I did 246 over 2 is 123, but that shouldn't be correct either. This should be 248 over 2, so this should be 124. I apologize about that. Notice I'm dividing by 2 because I'm dividing by n minus 1. In this case, my sample size was 3. 3 minus 1 gives me 2. So my variance is 123. All right, your turn. Go on and pause the video, calculate the variance for these 3 numbers. All right. So first step, I calculate the mean to be 38. After I subtract the mean from each of the values, I get 9, negative 2, and negative 7. After I square all of these, I get 81, 4, and 49. After I add all of these together, I get 134. But hey, you should probably double check me. Didn't go so well in the last example. And then after I divide this by n minus 1, I get my final result of 67. The variance for this data set is 67. And again, what you can see if you look at that final equation is all I'm doing with these steps is breaking these into pieces so that that final formula isn't quite as intimidating. Could I type all this in a single line in a single formula? Absolutely. But to me, that's a little bit scary and intimidating. So all we're doing is breaking that numerator into multiple steps. Subtract the mean first, then square, then add together, so that we can make that equation a little bit more accessible. All right. Well, the standard deviation, recall, is very related to the variance. The variance had this problem with the units where the units were units squared. The standard deviation just says, well, if the units are the units squared, let's take the square root of that to get rid of the squared and get us back to the original units. And that literally is what we do. We simply take the square root of the variance to find the standard deviation. The formula for it is as easy as it sounds. If s squared is the variance that we looked at before, we take the square root of that to get to s, the standard deviation. So again, if my variance was in liters squared of blood, now my standard deviation would be in liters of blood. That's a lot of blood, so hopefully not that much. And again, when I say units is a bit abstract, but units can be anything. It's not just liters of blood. It could be inches. It could be people. It could be millimeters of mercury. It could be whatever. So let's try a couple examples to close out here. So standard deviation of the below data set. This will be the one I try, or you can pause it and try it yourself. Here, again, we previously found that the variance was 124. Ooh, see, I got it right here. The standard deviation, if I take the square root of that variance, I get about 11.14. So all I do is take the square root of that original variance term. That's it. That's it. That's it. All right, now you give one a shot using the variance you found in the previous slide. So go on and pause the video and give this one a shot. Find the standard deviation. All right, coming back to it. We have the square root of the variance you found previously. That was 67. Square root of 67 gives us about 8.19, and that is the standard deviation of this data set. Standard deviation, the interpretation of standard deviation, it's in those same units. But what does it mean? Well, even though it's in the same units, the meaning is a bit shifty. One good gut meaning is that if we look at the mean plus 2 standard deviations and the mean minus 2 standard deviations, roughly 95% of the data falls within whatever those two numbers are. So mean plus 2 standard deviations is the top end, mean minus 2 standard deviations is the bottom end, and again, about 95% of the data falls within those two values. So that's a good, that's one of the ways that we use the standard deviation in statistics actually is that distinction. So that can be potentially helpful to understand. And that closes us out for today. So this has been a lecture set on some basic statistics. Again, these are some calculations that we will be using and referring back to through the rest of the course. So if you have any questions, as always, please feel free to send me an email. Check out the Canvas page for more help. If you find more help somewhere else, that's fantastic. I am so happy for you. Again, send me an email. Let me know what worked for you. But my goal is for you to learn the content. So that's our goal here. Don't forget, in this lecture set, accompanying this lecture set, are some videos demonstrating how to do this in software. So please do check that out. I believe the software we're using for this class is Excel. So please do check that out so that you can see how we do this in Excel so you don't have to do all this by hand. If you've been working with me with a calculator, that's good. I think that really, really helps you to understand kind of what's going on in the back end. But those software videos are going to help you to understand how to do this quickly and efficiently so that when you're doing your homework, you won't feel like you have to do a whole ton of hand calculation. And that'll be it for today. So I look forward to seeing you all in the next video.